Hi, my name is Benjamin Douglas. I am the technical lead for search infrastructure at Yelp, and I'm here to talk to you just a little bit about data hydration. Really quickly, for those of you who are not familiar with Yelp, we're a platform that connects people with great local businesses. This is done primarily through reviews that the users of our platform um, use businesses and review them on the platform and use that information uh, to discover other businesses and which ones they want to use. As of last year, we have about 250 million different reviews and 31 million active users. So in short, we have a lot of data and a lot of users that are looking for that data. And that's where the search team comes in. So to give you a little context about what kind of challenges we face, this is a sample a search result snippet. Potentially, this was a user who was looking for restaurants or Italian restaurants, something like that. And even though it looks pretty basic, there actually are quite a lot of different pieces of information in this snippet that turns out they come from a variety of different places. So for example, the name and address and number of reviews might come just out of a single column in a database. But something like the photo to show, which has to be picked from potentially thousands of photos, is a much more complicated process that will involve potentially a machine learned model or fetching data from a number of different databases, et cetera. And essentially what we're doing on the search infrastructure team is trying to make this process as efficient as possible. So it's taking essentially the output of a lot of good work by our data teams for things like the machine learning models and serve them as quickly as possible, basically thinking in terms of milliseconds, like how fast can we assemble this page and display it. So this process has gone through a number of different iterations. The first one was very simple, and we fetched all of the data in real time as the users were asking for it. So in this very simplified flow here, you can see that a user, either from the website or the app, talks to our main microservice, which then calls a subsidiary microservice with all of the logic for fetching the data, applying the models, and so forth. As the models have gotten more complicated and the number of different elements that we show has increased, this has become a bottleneck for showing search results. So we were trying to take a look at how we can speed up this process. The first thing that we tried is sort of what everybody does, is we added a cache. The idea here is that once we have calculated this, this property for a certain business, we put it into the cache so that if someone else asks for it, they can get the pre-computed version instead of going to the backend databases. Turns out this works pretty well for businesses at the head of the distribution, that is, those that are searched for often. But there's a long tail of businesses that do not get searched for often and that will not end up being in the cache enough to help their performance. So we took a look at this and tried to figure out how can we increase the speed of fetching all of the businesses, not just the ones at the head of the distribution. So what we came up with was essentially a cache with 100% hit rate. That is, we don't actually go and fetch the hydration logic at runtime. We pre-compute it offline so that when a user asks for it, it's already been pre-computed. This is kept alive by having an indexer listen to changes in our SQL backends. And whenever we detect a change in a row in one of the databases, we reissue the hydration logic for that business and feed it into the materialized view. This process has greatly impacted and sped up our fetching time, but operationally, keeping this up and running has been problematic, which I'll explain here. So essentially, we built this up as an ad hoc system that was not integrated with much else inside the Yelp ecosystem. And some of the features that we really wished it would have, and some of these questions that we wished would be easier, simply weren't possible. So with respect to change management, this was a very difficult process, and we had no idea really how to quantify a change in our hydration logic. That would be, for example, a new machine learned model was uploaded, or some logic changes happened. We really had no idea how many properties and in what way that would change. Would we need to backfill if we had a change in the code? Would we need to backfill everything, or just some businesses? How many properties are affected? That kind of thing. We just didn't know, and it was a very it was a process that just required a lot of in-depth information that didn't migrate very well with new people joining the team. There's also no introspection or history into this. The materialized view is a key value store, and all we know is that at any one given time, a certain key has a certain value. We don't know how that changed over time. We don't know at what point it was added. And especially if a row gets deleted, for example, in an incident, if some piece of information is missing, we have no idea when it left. So with all of these problems, we started talking to other groups within the company if they had how they were treating these kinds of issues. And interestingly, it brought us all the way back to our data teams. So there is a pretty sophisticated ETL pipeline that has been built up over the years at Yelp called the Yelp data pipeline that is used primarily for backend and offline data work, things like log processing and collecting data for machine learned models, running those machine learned models, training them, etc. And after taking a look at it, we realized that this would be a perfect fit for our use case as well. So to take a look at the modified architecture, which is what we have today, is that instead of having an ad hoc process feed our materialized view, we actually put it into our production, mostly used for offline data pipeline. There's a lot more information about how the pipeline works on the Yelp engineering blog, but just to give a very brief summary, it is based on Kafka, where the data is flowing from different sources into Kafka streams, and then it uses Flink as a transformation layer to apply transformations to that data, which is exactly the kinds of things that we needed in retrospect. So now that we have this data pipeline in place and a proper ETL pipeline, how has that helped us? Well, the first and biggest thing is that it helped our change management. That it's now much more clear what changes in the code affect which properties and in what way. This is something that we get owing to the organization of the code and how all the data is separated by different streams. The streams are also schematized, which means we know the form of the data and whether something is violating those schemas. And also this process gives us much better tracking of incidents. So for example, we can feed all of this data seamlessly into another data store like Redshift or our data lake and query it for things like, hey, when did this value change and what was the process that made that change, which is something we couldn't do before. And lastly, we have a lot more functionality that our old system didn't give us, things like rewinding it in time and snapshotting it and that kind of thing. Yeah, so that's about it. I just really wanted to go over an example of how some data processing pipelines that normally are associated with offline work have been modified to serve our production traffic. So I definitely encourage you all to go and read more information from our blog, or you can reach out to me directly. Thank you very much.